Hello everyone. In this video, what we're going to cover is scientific notation. So you'll find in these slides that I have lots of different topics, but I'm going to split each of the videos I record from these slides into their individual topics. That way, if you want to go back and just find one specific thing, I think it'll be a little bit easier to find that. So in these slides, we're going to talk a bit about, or in this video at least, we're going to talk a little bit about scientific notation, why it's important, why we use it, and how to go in and out of scientific notation. So enjoy. So that being said, we're going to go ahead and get started here, and I want to point out why a lot of this stuff is important and why we care so much about it. And it starts with a little bit of a tale. So in 1998, NASA launched a Mars orbiter. Everything seemed to be going great. We send the orbiter out, it's getting to Mars. They're monitoring its progress as it's heading towards Mars, and all of a sudden, when it got to Mars, it crashed because it entered the atmosphere too low. How in the heck did this happen? Well, in the end, realistically, it was because someone forgot to write down their units, okay? So the orbiter itself was programmed to accept metric units by the computer programmers that put it together. However, the engineers that were sending the commands to the orbiter actually sent the commands in English units, or what we might call imperial units, if you're as old as I am. Because that happened, the orbiter thought it was getting meters and centimeters. The engineers sent the commands in feet and inches, which are very different things. A meter is much closer to a yard or 3 feet, and we sent it in feet. Yay! So the orbiter crashed. That was a multi-million-dollar experiment that we were sending to Mars. We lost all of the money, all of the potential science that could have come with that, and boom, no more Mars orbiter. So some engineers that day had a really, really bad day, let me tell you, and that's not what you want to have happen as an engineer. So it's really important that we learn how to communicate with each other as scientists so that when you see a number, you know exactly what I mean, and when I see a number you write down, I know exactly what you mean as well. So it's really important that we get these things worked out, and this is one of the reasons why, is because we can have really, really, really easy to fix mix-ups if we would just actually talk to each other the way we should. So we want to know how scientists are actually going to talk about these numbers so that this doesn't happen again. Well, first and foremost, one thing that scientists like to do so that we can communicate to each other better is find different ways to write down really, really big and really, really small numbers. So scientists often work with very large or very small numbers. These are some examples of some scientific numbers that are extremely large or small in size. So just as an example of like kind of some of the stuff you might run into if you were having to deal with these numbers the way they look this way, right? Like it's really hard for me to be able to like compare the speed of light to Avogadro's number if I ever just wanted to know how big they were in comparison to each other, right? Because there's 1.5 million zeros here, and there's a few here, and I don't know exactly what this means, kind of where it's coming from, kind of a deal. So it's hard to see exactly how much bigger Avogadro's number is than the speed of light, for example, or how much smaller the radius of a gold atom is in comparison. So we really need a way to talk about these numbers that isn't so clunky with all these zeros. And this will be a theme throughout the whole semester, aka scientists are lazy, right? So we don't want to have to spend so much time writing down so many zeros because it's just a waste of time to sit there and write and write and write and write and write when we could have some sort of shorthand notation that helps us with this instead. I want to get back to my science. I want to get back in the lab running experiments and collecting useful data rather than continuing to have to sit here and write down number after number after number after number after number with 1.5 million zeros, okay? Also, as I pointed out before, it's really, really hard to compare these extremely large or extremely small numbers on site because of all the zeros. It's hard for me to tell exactly how many more zeros this number has than this one, and it's because it's really hard to just see that with your eyes, so it's really important that we find a way to express these numbers such that we can actually read them and we can, boom, compare immediately on site how they look and how much bigger one or another is than the other. So to do this, we use something called scientific notation. So it's a way to report really large or really small numbers so that they become easier to read and we can compare them much easier. So we're going to take any number we have and break it into two parts. We're going to have a decimal part, some number between 1 and 10, okay? So it's only in proper scientific notation if it's between 1 and 10. And then the exponential part. So the exponent piece is going to be 10 raised to some number. In this case, we're calling it n. So on your screen, you can see an example of scientific notation. So you can see we have the decimal part here in the yellow on the left, and that's 1.2. Okay, so that's a number between 1 and 10. 1.2 is between 1 and 10. So we've got a decimal part here, and we have an exponent part over here, an exponential part. So we have times 10 to some sort of exponent. So really what's hidden in the scientific notation and what it's telling us is if I literally take 1.2 and I multiply it by times 10 to the minus 10, that is what my original number is. So if I happen to multiply this out, I get 0. All of these zeros, 1, 2. Okay, so what it's telling us is how much we need to shift the number by to kind of get it back into its original position. So it makes it really easy to see things on scale because we can just compare those exponents and we can see, oh, this one's times 10 to the minus 10. I might have something that's times 10 to the 10. So I can see how big those are different than each other, or times 10 to the 8 versus times 10 to the 9. If a big number is off by just 1 0, it's so much easier to see that in the scientific notation form than it is how we generally write numbers with all those zeros, okay? Because it'd be hard to tell if I had something times 10 to the minus 9 written here next to this. It's only going to shift it a tiny bit. It'd be hard to visually see that very quickly. So, to be absolutely clear, scientific notation is just shorthand notation. It is only a way of representing a number or reporting a number. It does not change the number in any way, shape, or form. Scientific notation does not change the value of the number, so it still is the same number it started as well as it does not change the unit of the number you're looking at. So nothing there, if we're just expressing it as scientific notation, is ever being changed about the number. We're just writing it in a different way, right? So it's just like changing the branding or something like that. Okay, so let's talk a little bit about what we're doing when we're talking and we're trying to actually put a number into scientific notation. So what we want to do is find the decimal part, then find the exponent part. So the first thing you do is you move the decimal point so that you have a number between 1 and 10. So we've got two different example numbers down here. We have 0.00034 and we have 5,983. So the first thing we're going to do when we're attempting to put something into scientific notation is to move that decimal point such that we have a number between 1 and 10, okay? So this number is not between 1 and 10. If I move the decimal point here in between the zeros, it's still not going to be a number between 1 and 10. The same thing here, and the same thing before the 3. But if I put the decimal point in between the 3 and 4, I now have a number between 1 and 10, aka 3.4. So I'm going to move that decimal point such that I have a number between 1 and 10. And then in this case, if my imaginary decimal point is over here at the end, what I'm going to do is start to move it backwards until I have a number between 1 and 10. So I'm kind of moving it this way, and it looks like if I put it in between the 5 and the 9, I have 5.983. So 5.983 is a number between 1 and 10. So again, if you want to move that decimal part so that it's it's a number between 1 and 10. So you'll see at different points in the semester, we might come across something that's not really proper scientific notation. Sometimes scientists will write something like 563 times 10 to the 6th nanometers or something like that. And yeah, we do that. Is it really technically correct? No. But do we do it? Yeah, kind of a thing. So you might see something that's improper, but we're going to focus on being able to properly write scientific notation. So again, if I have 5.983 here, that's a number between 1 and 10. Oops. And so is 3.4. 3.4 is a number between 1 and 10. Okay. So once we have our decimal part, we want to find the exponent part, right? We got to find the times 10 to the whatever. So what we do first is we count how many places we had to move the decimal point. Oops. Count how many places we had to move the decimal point. So if we're focusing on 0.00034, and I look at where I moved my decimal point to, I moved it 1 spot, I moved it 2 spots, I moved it 3 spots, and I moved it 4 spots to get to that 3.4 kind of looking number, right? So I moved it 4 spots. So that means my exponent part is going to be times 10 to the 4. However, we have to determine whether that exponent is going to be negative or positive. If you start with a number between 0 and 1, it's going to be a negative exponent. If you start with a bigger number, like this one, it's a positive exponent. Because what you're doing is you're saying times 10 to the minus 4. So 10 to the minus 4 is a very small number. So if I multiply 3.4 times a little teeny tiny number, it makes that original number small. Or it makes that decimal number become small to get back to your original number. So if I start with something that's between 0 and 1, what I'm going to find is the exponent is going to be negative. If I start with a number that's greater than 1, I'm going to find that that exponent is going to be positive because I want to multiply by a really big number. 10 to the 3 is 1,000. That's a pretty big number. So I'm taking 500 or 5.983 times 1,000. So it's a bigger number. So then I can say, okay, I can get back to a bigger number again. So if your exponent is positive, you started with a number that's greater than 1. If you have an exponent that's negative, you've got a number that's between 0 and 1. Okay, so really small decimal numbers get a negative exponent. Bigger numbers get a positive exponent. So again, I got the 4 because I jumped the decimal point 4 spaces so that I could make it look like a number between 1 and 10. And I got the negative sign because this original number is between 0 and 1. Over here, I started with my decimal point over here and I put it in between the 5 and the 9. So I jumped 1 space, I jumped 2 space, I jumped 3 spaces to move my decimal point. So that means the number of the exponent is 3. And then I decide, is it positive or is it negative? Well, because my original number was greater than 1, it's going to be positive. Okay? So that's a little bit about how we do scientific notation, and we'll get some practice in with that in just a second. So that being said, you can always kind of use some sort of self-check to get yourself back out of this scenario. So if we're looking at that 1.2 times 10 to the minus 10 that we were talking about before, we could think of that as 1.2 times 10 to the minus 10, which looks something like this. And then that's going to equal 0. All of these zeros, 1, 2, right? So you can kind of use this as a self-check. So if I have an original number and I re-multiply it back out, or I do my scientific notation, then I multiply back through by my scientific notation, I should get back to the original number. So here we can see that we have like this number we were just looking at on the other screen. What we're really saying again is it's 5.983 times 1,000, which is the same thing as 10 to the 3. So basically we're just hiding, again, all of those zeros in some sort of exponent there. Okay, so let's go ahead, let's work through some examples. I just would like to point out that I'm mostly worried that you can put a number into scientific notation and you understand what that means when a number's in scientific notation, okay? So while I am going to give you some examples of how to take a number out of scientific notation, I really care more that you know how to put a number into scientific notation, okay? So that being said, let's work through some examples. So on example number 1 here, we have a really big number, and we're going to try to put that into scientific notation. So remember, the first step is always to make sure you write the number so that it looks like a decimal between 1 and 10. So this would be like 9.38459. Okay, so that's how I make that number look like it's a decimal between 1 and 10. I write down all of the non-zero numbers I see, and I leave everything else the same. So when we're talking a little bit later about significant figures and things like that, I want you to remember kind of what scientific notation is, and that, you know, we're just hiding a bunch of zeros in scientific notation. So anyways, let's continue on. So I've put my number between 1 and 10, so I've taken my decimal point, like a hypothetical decimal point from over here, from over there, and I've swooped it all the way up and under over here, okay? So my next step is to go ahead and determine how many spaces I moved to that decimal point. So let's count. Because remember, I need to write down times 10 to a number, so let's figure out what that number is. It's how many spaces we moved to the decimal point. So this would be like 1, 2, 3 spaces. 4, 5, 6 spaces, 7, 8, 9, 10, 11, 12 spaces, 13, 14, 15, 16. So I moved it 16 spaces, so that means my number is 16. And I have to determine, is the 16 positive or is it negative 16? Well, anything that is between 0 and 1 of our original number is going to get a negative exponent, and anything between or above 1, a bigger number, is going to get a positive exponent. So because this is a really big number, we know that this is going to be like a positive 16 in the exponent. Okay? So my final answer here for example number 1 is 9.38459 times 10 to the 16th. Okay, let's get rid of this a little bit here. All right, so that's number 1. Let's go ahead and do example number 2 as well. So example number 2 says take 6.754 out of scientific notation. So let's look at the mechanics and let's write this down. So if I have 6.754 times 10 to the 2, I could write that as 6.754 times 100. 10 squared is 100, so I could write it down like this if it helps me figure out what's going on. And so I can go ahead and I can just type this into my calculator. 6.754 times 100 equals 675.4. Boom. So that's how I take that number out of scientific notation. So in scientific notation, it looks like 6.754 times 10 to the 2. When I take it out of scientific notation, that's just simply saying it's 675.4. Pretty straightforward. Okay, so let's go ahead and do example number 3. I'm just going to clean up my workspace a bit here. Okay, so we're going to do example number 3 now. So we want to take this really small decimal number and put it in scientific notation. So remember, the first step when we're putting something in scientific notation is to write the numbers so that it looks like it's between 1 and 10. So in this case, that's going to be 3.4872. So my decimal part is 3.4872. And I want to figure out times 10 to the what exponent? Well, again, to do that, I hypothetically put my decimal point here. So I want to know how many spaces it takes me to move that decimal point. That being said, we can go ahead and count. So we moved it 1 space, 2, 3, 4, 5, and 6. Okay, so I know that my exponent is 6. So the exponent is always however many spaces you had to move that decimal point so that it looked like the number was between 1 and 10, and in this case, I moved it 6 spaces. And then to determine whether that's positive 6 or negative 6, I go back to the original number that I had, and I decide, is it between 0 and 1? If so, it's a negative exponent. Is it greater than 1? It's a positive exponent. Well, I start out with this really, really small decimal number, and that number lies between 0 and 1, so that means I'm going to have negative 6 as my exponent. So to take that number and put it in scientific notation, it looks like 3.4872 times 10 to the minus 6. All right, let's do one last example here. We're going to do example number 4. So let's do it. So we want to take 3.97 times 10 to the minus 4 out of scientific notation, okay? So what this is really telling me is that I need to move my decimal point 4 places because that's the number in the exponent. I'm going to move it 4 places because that's the number in the exponent. And I'm going to move it so that the number gets smaller, okay? I'm going to move it so that the number gets smaller because I can see that negative there. Remember, a negative makes it a number between 1 and 0. So that's how I'm going to swing this. So that would be like saying I have 3.97, right? My decimal point starts here. I move it 1 spot, I move it 2, I move it 3, and I move it 4, okay? So I put it there. So if I wanted to take that number out of scientific notation, I could say it's 0.000397. So I kind of showed you 2 different ways there to take something in and out of scientific notation, or take it out of scientific notation. So I showed you one way when we did example number 2, and I showed you a different way when we did example number 4. Both are valid. If you think of scientific notation in another way that helps you, thumbs up. I'm happy for you. Please continue to do things the way that makes sense to you, as long as you're getting the right answer. Okay? So these are just some strategies for taking things in and out of scientific notation. But I always want you guys to do what works best for you. So, okay. I also have the answers here on the screen as always. So if you ever need to guess and check or work through the problems yourself, I always have a way for you to check against the examples I put in the slides.